With this video, we will start a new series of conversations which will be an English language version of my Spanish language cycle, Mitos y Verdades. It will be called Truth and Fiction and will be presented by my son, Bruno Anton, who is an English teacher and has been assisting me in the production of the previous videos.
In this presentation, we will try to demonstrate the mineral origin of hydrocarbons, especially natural gas and oil. We will start by presenting some data that will allow us to understand the conclusions later. First of all, we need to remember that hydrogen is the most common element in the universe, representing 73.9% of all the existing matter. In second place is helium, with 24%, but since it is a noble gas and does not combine with other elements, it's not relevant for this argument. Meanwhile, all other chemical elements combined are only 2.1% of the total universe. Within this large group of elements, which we define as the heavier elements, the two most important ones by mass are oxygen and carbon. Oxygen represents 1% of the entire universe, that is, almost half of the matter, excluding hydrogen and helium, while carbon represents approximately 0.46% of the universe, and thus almost a fifth of the elements that we have defined as heavier elements. It's not a surprise that since oxygen and carbon are the two most common heavy elements, their main compound, carbon dioxide, is the most abundant in some planetary atmospheres of our solar system, such as Venus and Mars. On Venus, CO2 is 96.5% of the atmosphere, and on Mars it is 95.32%. However, in spite of the similar atmospheric composition, the surface of these two planets is extremely different. On Venus, the atmospheric pressure is 93 bars, while on Mars, it's 10,000 times lower. Similarly, on Venus, the average temperature of the atmosphere is about 480 degrees Celsius, while on Mars, it's about 80 degrees Celsius below zero. However, as we mentioned before, despite these huge differences, the atmosphere composition in relation to CO2 is similar. It is striking that in the Earth, which is located between Venus and Mars regarding its distance from the Sun, the atmosphere has only 0.04% of CO2, which means that strangely it has 2,000 times less CO2 than the other two planets that we mentioned previously. It is likely that the Earth originally had about the same amount of CO2 as Venus and Mars. However, now it is much less. For that, a question arises. Where did the missing CO2 go? There is a logical answer to this question. The missing CO2 is stored within the limestones. These limestones, which are rocks made up of carbonates and oxidated carbon compounds, represent about 20% of the Earth's crust. Thus, this previously abundant CO2 in Archaeozoic times, over 4 billion years ago, was likely very abundant in the air and in the seas, and was thus used by a wide variety of organisms to make their skeletons and shells, which are generally made up of carbonates. These organic carbonates were deposited on the muddy bottoms of the oceans, and then buried by other deposits, and eventually consolidated into limestone rocks, thus sealing the carbon away in the earth. This limestone formation process depended on the evolution of life. There was a tendency for marine and aquatic carbonate-producing populations to increase both in complexity and extent, and for that reason limestone formation was less in earlier times. Therefore, there was less limestone formation and carbon capture in the Proterozoic era, a billion years ago, than in more recent times. For example, during the Mesozoic era, about 200 or 300 billion years ago. During the Mesozoic, the atmosphere contained much more CO2 than it does now, and probably had a much higher density, which could have facilitated the overgrowth of dinosaurs and insects. As proof of this, beyond the enormous dinosaurs themselves, fossil records indicate that during the Mesozoic, even insect sizes were many times larger than the ones seen today. Another issue to consider is that in the interior of the Earth, there is most likely a significant amount of carbon due to its abundance in the original nebula during the Earth's formation. At the same time, we remember that hydrogen is usually abundant practically everywhere, mainly because it is released from water in other hydrogenated compounds. From there, it follows, given the conditions of pressure and temperature in the Earth's lower crust and mantle, the carbon atoms can surround themselves with hydrogen atoms, forming methane and other hydrocarbons. This situation is thought to occur in the Earth at a depth of 50 to 100 kilometers. The methane that was, and is, formed in depth tends to rise, but generally the rock masses prevent its ascent. In any case, at some point, fractures may be generated, and through them the methane may rise to upper levels of the crust. Along the way, methane can undergo oxidation processes with oxides and sulfates, forming water with the hydrogen atoms and carbon dioxide when combining with carbon. As hydrogen oxidizes more quickly than carbon, the compounds are enriched in carbon, and what was methane becomes ethane, and then propane, then butane, and so on until forming heavier molecules, such as gasoline and tar. This oxidation process is often fired up by certain bacteria that live in the depths of the Earth, the hypothermobacteria. As the methane or other hydrocarbons rise, these surging fluids are loaded with helium that may have formed in rock formations that contain radioactive elements such as uranium. For this reason, in many places, natural gas contains helium that has nothing, absolutely nothing to do with the organic matter that those who support the fossil hypothesis speak of. In the ascent, both the methane and its derivative hydrocarbons can accumulate below impermeable clay or lava layers that prevent them from continuing to rise, constituting exploitable deposits through drilling. Notwithstanding, hydrocarbons often manage to ascend very slowly through impermeable or semi-permeable layers, for example shale, without being able to go through them completely, but remain embedded inside them. These hydrocarbons contained in the shale can be extracted by the method of fracking or hydraulic fracking, which fractures the rock and allows the fluids to rise. The conclusion of this conversation is that oil and its derivatives are of mineral origin, and they are coming from the depth of the Earth. Also, it can be deducted from these observations and data that the carbon dioxide content in the atmosphere is extremely low, really extremely low, and consequently that almost certainly it doesn't have any significant effect on the Earth climate change that could be detected.